So, hello student. So, now we are on module 9 biological transformation second and we will talk anaerobic digestion process. Here we will have 3 lectures on anaerobic digestion process, and in this module I will discuss about what exactly meaning of anaerobic digestion process. There are different type of different stages, different factors affecting, and also the commercially available reactors. Okay. So, we are at the transformation. So, this today's lecture on definition, stages and factor affecting anaerobic digestion process. So, first we will go for definition. So, like the composting process, I explained that is a aerobic process. So, degradation of organic matter under aerobic condition, that also you can say is a composting process. So, similar way the anaerobic digestion is a controlled process involving microbial decomposition of organic matter in the absence of oxygen. This was provided in our Municipal solid waste manual 2018. But if you go the technically, the anaerobic digestion involves the process of decaying organic matter in the absence of any terminal electron acceptor like sulphate, nitrate or oxygen. So, is a absence of any terminal electron acceptor, and in this case the major electron acceptors are oxygen, or in the same way we can say the absence of oxygen. Anaerobic digestion consists of number of complex biochemical reaction carries out by several types of microorganisms that survive in oxygen free condition. During this process the biogas is produced, which is mainly composed of methane and carbon dioxide as a major gases with trace amount of hydrogen sulphide, nitrogen and water vapors, but the major compositions are methane and carbon dioxide. The material left over anaerobic digestion process is called digestate. Okay. This you remember, we will also have discussion on digestate, which is rich in nutrient. So, normally the many literature suggests that whatever the leftover or whatever is the outlet from the anaerobic digestion process can be used as an compost or as an fertilizer, because it will be rich in nutrients. Digestate is a wet mixture that can be separated into solid and liquid. So, now here this is the digester. If you feed organic matter, and finally we will get digestate as a outcome of the reactor. Along with that the biogas will generate, and this biogas majorly will be the methane, is a highly combustible gas, and along with the carbon dioxide will be also there because of degradation process. So, this biogas is a renewable energy source that can be used as a fuel, can be used as a variety of ways of production of heat and electricity. These biogas directly can be used in the kitchen for cooking purpose, directly we can use without any separation. Only the problem is that this carbon dioxide is highly corrosive gas. So, if that percentage is low, then easily we can use directly this biogas for a cooking purpose. So, whatever here the directly we can use for heat production for cooking process through biomethanation process. Biomethanation process means the separation of carbon dioxide from the biogas. Directly this gas we can put it into the gas grid. Okay. Or directly this methane, if we are getting 95% of methane, means we can call it as a bio CNG. So, normally whatever the CNG is available, that contained 95 to 98% of methane, but that is chemically produced methane. Now, here through this biogas also, if you are able to remove the carbon dioxide from the biogas and other gases like hydrogen sulphides, hydrogen or ammonia and can come up with methane percentage 95 to 98% also can be used as in fuel. And same this biogas also can be used for electricity or power production also is possible. A range of anaerobic digestion technology convert livestock manual, municipal wastewater solid, food waste, high strength industrial wastewater and residual fat, oil, grease and various organic waste stream into biogas. So, this anaerobic digestion process is very popular in the wastewater treatment process or not only for the sewage treatment, but also for industrial wastewater treatment also is anaerobic digestion process is highly popular. Why it is very popular? Because sludge production is very low in anaerobic digestion process is like I talked about composting process where the glucose degradation to the compost or that final sludge that will goes up to 30%, but in the anaerobic condition whatever the sludge will produce that will have only 5%. So, sludge production is low, that is the major benefit of the anaerobic digestion process, and this anaerobic digestion also can take high BOD5 wastewater. So, like in the aerobic system for wastewater treatment or sewage treatment, in the aerobic system we can go up to 200-300 milligram per liter BOD5, but in the anaerobic system we can go up to 700-800 milligram per liter BOD5 value. That is and there are a lot of successful and various scales of anaerobic digestion process are available for the sewage treatment and some other industrial wastewater treatment process. Similar way for anaerobic digestion process also is very popular for the organic waste that is solid in nature. But again that directly we can't go for the solid one, we have to make that particular material as an slurry kind of material and then easy to go for anaerobic digestion process. So, some facts if you see that in 17th century the first found out the decaying of organic matter could result in flammable gases. So, first anaerobic digestion plant was built in Mumbai, India in 1859. So, you see here is very old process, we are knowing this anaerobic digestion process. Maybe I think you also heard of sometimes gobar gas plant, even in 90s when I was very young, I was in the school and especially in the rural areas we used to see number of gobar gas plants, and these gobar gas plants specially for the production of biogas for cooking purpose and highly successfully running these kind of plants was available. But now I think most of the places those plants are not working because of different issues. So, when you talk about the composition of biogas, your methane percentage can go up to 70% also is possible, but if you have a properly designed reactor can achieve 65 minimum 65% of methane. Carbon dioxide could be 30 to 60% and other gases is in between 1 to 5%, but the proper reactor these percentage of other gases never increase 1% or 2%. So, when you see the relationship of methane and carbon dioxide, so this is the time versus the biogas. So, methane percentage is more and carbon dioxide percentage is low, and you see here there is a change in or lower down in methane and increase in carbon dioxide in two different places is because of feed. Because time to time we will feed the reactor, feed the unit with the fresh organic matter. So, these kind of things are possible, and at particular time it is possible that carbon dioxide percentage will be more if there is no proper anaerobic condition achieved. So, at 44% of carbon dioxide, if that is getting out from the reactor, there will not be any burning or there will not be any flame is possible. Means the reactor are generating more than 45% of carbon dioxide cannot be useful for cooking purpose. Okay. And this is what the problem with those gobar gas plants. I think the feed has been changed because they were working onto the cow dung or mostly onto the cow dung, but later on the other kind of feed also has been utilized in the biogas plants like kitchen waste, other festival, during festival. So, large amount of organic waste is getting generated and that also has been disposed into the this reactor, and this entire reactor become acidified because you know that kitchen waste highly acidic in nature. So, because of that the carbon dioxide percentage has been raised and those kind of reactor never has been again came back in the same conditions. If you see the stages of anaerobic digestion process, it will have 4 different stages of digestion process. First is the hydrolysis. So, hydrolysis is nothing but a simple breakdown of complex organic matter, like hydrolysis process means cooking is also in nature, household also is a one kind of hydrolysis process, or we can say is a pre-treatment of process. So, why cooking is very important? Because that particular substrate we can't digest or humans can't digest very easily. So, if you go for cooking means we will hydrolyze it and convert that food into the very simple material which is very easy to get digest by the humans. Next is the acidogenesis. Okay. So, here majorly the all basic monomers will convert into volatile fatty acids, but these volatile fatty acids will be mostly the propionic acid, butyric acid or valeric acids, and this was somewhat large carbon containing fatty acids. Okay. That is in acidogenesis, and acidogenesis followed the acetogenesis. Okay. So, only change in the both the stages. So, in the acidogenesis this propionic acid, butyric acid, valeric acids will produce, but in acetogenesis these acids will be break down and convert in acetic acid, and finally from acetic acid we will get methane and carbon dioxide as an final product as in biogas. And the important fact is that in all the stages the microorganisms involved in each stage. So, if you simply can say that what kind of microorganism. So, for these acidogenesis, acetogenesis, normally those bacteria we called as a acid forming bacteria, because here major production is acid production, and the methogenesis stage normally that is a second stage, or if you take the first stage is the hydrolysis, second is the acid forming stage, and third stage will be the methane forming bacteria. These are the more abundant should be there in the reactor. So, here you can see that complex organic matter through first stage is hydrolysis, second stage is acidogenesis, third is acetogenesis, and fourth is methogenesis stage will be arrived. So, in hydrolysis the hydrolytic bacteria using extracellular enzymes are involved, those microorganisms. In acidogenesis fermentative or acidogenic bacteria will work, and the acetogenesis this acetogenic bacteria, but the group of these and this called as a acid forming bacteria, and finally in methogenesis we will get methogenic bacteria or methane forming bacteria. So, what is the role of microbes in anaerobic digestion process? So, now here you see that So, here I made it one particular flow of degradation process. So, biomass will get after hydrolysis process, it will produce fatty acids. So, this propanic acid, butyric acid or other acids will produce, and parallelly this acetic acid also will produce. Okay, and finally, this is both will be together, and again this propanic acid or butyric acid will convert into acetic acid, and finally biogas will produce. And you see here by color, this the yellow color by production of fatty acids will by acidogenic bacteria. Okay. And green color you will see that is acetogenic bacteria. These bacteria are required to convert from the large carbon containing fatty acids to the simple carbon containing as fatty acids. And finally, methogenic bacteria from this same acetic acid, it will convert into methane and carbon dioxide. So, if you see the COD balance or chemical oxygen demand, nothing but is a organic matter in anaerobic digestion process. So, your 90% will utilize for the biogas production, and only 10% will goes to the sludge production or digested production. That is why the anaerobic digestion process is highly beneficial process. So, again the different stages of anaerobic digestion process. So, the first is hydrolysis process. In this process, the insoluble complex organic matter such as protein, polysaccharides and fats are converted to soluble monomers such as peptide, fatty acids and saccharides. So, that is the first hydrolysis process. Okay. So, where this entire the simpler monomers means amino acid, sugar and fatty acids. So, it is a slow process. This stage is a rate limiting stage in the anaerobic digestion process. This is very important to know that in anaerobic digestion process which stage is a rate limiting stage is a, and if you know the rate limiting stage, we can work more onto rate limiting stage, or you can find different solutions for this rate limiting stage. So, the hydrolysis is a rate limiting stage in the anaerobic digestion process. So, because it is a rate limiting stage, so many time if you feed the waste into the anaerobic digester or in the reactor, we already will go for mechanical shading or grinding. This mechanical grinding means we will convert the entire particle to 3 mm, 4 mm size. Like in the composting, I propose that to have the size of 1 centimeter or 2 centimeter size is good for the bacterial degradation process. So, here if you reduce the size of 3 mm, 4 mm size is highly beneficial for the anaerobic bacteria. So, mechanical grinding, that is a one kind of hydrolysis process or pre-treatment process, and directly the material will go to the acid forming stage. So, what are the biochemical reaction involved here? The whatever organic matter will hydrolyze and will convert into simple monomers. Now, the next stage is a acidogenesis or fermentation process. So, in this process hydrolyzed products are converted into simple molecules with a low molecular weight such as volatile fatty acids like propanic acid, butyric acids, valeric acid and alcohols, aldehydes and certain gases such as carbon dioxide, ammonia and hydrogen. So, this is what the second stage, and this stage is affected by diverse group of bacteria which is capable of bringing down the pH inside the reactor to 4. Now, this is also very important fact in the anaerobic digestion process, because these bacteria are one of the strongest bacteria in the degradation process under anaerobic condition. So, because of production of this acetic acid, propionic acids, although is not very strong acids, these are the weak acids, but because of this acid production there is a chances of a drop in the pH of 4. Now the problem, once the pH is acidic, very difficult to produce the methane gas in such condition, or there won't be a possibility of growth of methogenic bacteria or methane forming bacteria at this low pH. So, what biochemical reaction involves? The acid formers, and finally, it will convert into the fatty acids. Now, the next stage is a acetogenesis. In this process, the products of acidogenesis stage are converted to acetate H2 and CO2 by acetogenic bacteria. Okay. So, now here the production of acetic acid is a major along with the hydrogen. So, based on metabolism, there are two groups of acetogenic bacteria. The first is proton reducing acetogenic bacteria or H2 forming bacteria generating acetate, CO2 and H2, and next is acetate oxidizing bacteria or homoacetogenins catalyze acetate conversion to CO2 and H2. This stage can be regarded as a preparation stage for methogenesis and mostly a major biochemical reaction carried out by acetogens. So, what will be the reactions here? Could be CO2 plus H2 is CH3, that acetic acid production. Now, the next stage is, our last stage is methogenesis. So, this is the final stage in the anaerodization process, in which methogens create methane from the final product of acetogenesis as well as from some of the intermediate product from hydrolysis and acidogenesis. So, finally, methane production. So, there are two pathways to create methane. The first is this acetic acid, means CH3COOH is converting into methane and carbon dioxide, but remember that this process could be only possible at neutral pH, and again the problem is that the methane forming bacteria is not that strong as compared to the acid forming bacteria, and that is why the buffer or buffering capacity always need to be discussed in the anaerodization process. So, this buffering could be possible that if some kind of alkalinity could generate in the reactor, that is highly beneficial, or some amount of ammonia production also could be highly favorable in the reactor. So, that the neutral pH could be possible to maintain for the growth of methane forming bacteria or methogenic bacteria. And there are other way, by that way methane will produce, that is this carbon dioxide can be react with the water and will produce, but I think we did not find much literature that this pathway could be possible, but major pathway is this way, where acetic acid is degrading and converting into methane and carbon dioxide. Now, once we know that different stages of anaerodization process, now we will go for factors affecting anaerodization process. So, first is temperature. These parameter plays a major role in physical chemical property of substrate, which affect the thermodynamics and kinetic reaction inside the reactor. So, anaerobic process can be occur at wide range of temperature, which can be grouped as psychrophilic less than 20 degree, mesophilic 20 to 45 degree, and thermophilic 45 to 65 degree centigrade. So, if you see here the growth rate of methanogens, at which temperature the methogens will be grow fast. So, you see in the psychrophilic, you will not get much growth of methogens, this is the methogens, and in mesophilic is a okay production of methogens, but in the thermophilic condition like temperature more than 45 degrees centigrade, there is a very good chances of production of more methogens. More methogens production means more methane production in the process. So, rate of reaction doubles for every 10 degree centigrade rise in the temperature up to an optimum, after which reaction rate decline rapidly. Now, thermophilic temperature range generally has several effects over the lower range. Some positive effects are increase in the hydrolysis soluble products, which make them more accessible to the microorganism. That is one very important benefit of thermophilic temperature range. Increase reaction kinetics in both chemical and biological process, shortening the reaction time, hence the HRT of the reactor, hydraulic retention time. This is also important fact of the anaeroidization process. If suppose the HRT or hydraulic retention time is more, normally in commercial reactor we find the HRT of 25 to 30 days, means you will be required very large size of reactor for low quantity of organic feed. So, as an engineer I think we need to work more on to reduce the HRT. So, this is also good idea if you increase the temperature in the reactor. Improves the physiochemical properties of the soluble substrate, but there are some negative effects of thermophilic temperature, that increase the fraction of free ammonia, which is inhibitory to the, is not good for the microorganism. Ammonia inhibition could disturb the whole anaeroidization process dynamics and may hamper the quality of the gases. Reactor stability reduce, high accumulation of VFA occur, which affect the growth rate of methogens. So, there is possibility that in the thermophilic temperature the production of volatile fatty acids will be more. If this concentration goes to 2000, 3000 milligram per liter or even more than 4000 milligram per liter volatile fatty acid production. So, that is also not good for anaeroidization process, although we required volatile fatty acids for production of methane, but the high concentration also highly inhibitory for the anaeroidization process. And effluent quality reduce and toxicity increase the certain type of substrate. But for mesophilic temperature range, what are the advantage? Greater process stability, better richness in anaerobic bacteria, and disadvantage is that the yield that won't good as compared to the thermophilic one. But the optimum temperature range of anaeroidization can be hydrolysis in thermophilic range and methogens in the mesophilic range, but various other factors also need to be ascertained before deciding the range of temperature for anaeroidization process. So, here what it is explaining that why not the hydrolysis could do at thermophilic range and the methogenesis will be in the mesophilic range. So, that many times like I explained about the mechanical grinding, that is a hydrolysis process or pretreatment process. In this case what it suggested that in the hydrolysis increase the temperature for hydrolysis process, okay, and followed by the whatever the anaeroidization process you do it at mesophilic temperature only. So, there are many research papers available where the substrate is kept in the oven for getting the thermophilic temperature, had been used for different way the temperature has been added into the mass. So, that the hydrolysis could be better followed by anaeroidization process, that is under the mesophilic temperature. Too high your temperature may cause the metabolic rate to decline and due to degradation of enzyme which are critical to the life of the cell. Now, next parameter is a pH. This parameter affects the overall efficiency of the digestion process. So, as I was telling that methogens are very effective at a range of 6.5 to 7.5 means neutral pH. The pH varies due to parameters such as VFA, carbonate concentration and alkalinity of the system, also by a fraction of CO2 produced during the anaerodization process. So, time to time we have to monitor the reactor, how the pH increase or reduction is possible in the reactor. To maintain a constant pH, it is essential to control the relationship between the VFA and carbonate concentration, thus the maintaining the buffering capacity of the biogas reactor. So, one of the risks of the digester failure may be related to excessive accumulation of volatile fatty acids in the biogas digester. So, this is what I was telling about. If there is a excessive amount of VFA production, because of the pH will drop drastically. So, that could be a one of the risk of failure of biogas reactor. The acidogenesis bacteria then flourish at this low pH. The acidogenic bacteria will flourish, lowering the pH 5, inhibiting growth of methogens. So, in this case the major production of gas will be carbon dioxide, not methane, and you know that if carbon dioxide percentage more than 44%, so it will not be a combustible gas, and pH more than 8 proves to be toxic to most anaerobic bacteria, which inhibit biological fraction of anaerodization process. So, here important is that to maintain the pH, and this is possible by addition of mix of different organic residues. So, suppose kitchen waste if you are planning, so it is good to mix with the other kind of material which will maintain the particular pH, or your reactor has to be acclimatized into the neutral pH, and slowly these acidic kitchen waste could be feeded into the reactor, not at very high rate, and by looking and checking the reactor pH. So, there are two main operational methods for correcting unbalanced low pH condition in the digester. The first approach is to stop the feed and allow the methogenic population time to reduce the fatty acid concentration, thus raise the pH to an acceptable level of at least 6.8 or more than 6.5. So, the first approach is that do not feed the reactor, stop the feeding, so that the microbes will have more time to reduce these volatile fatty acids. Once you know that pH has been modified by reduction of volatile fatty acids, again we can start the feeding of the reactor. Second method involves the addition of chemical to raise the pH, which can provide the additional buffering capacity of that particular mass. And what is the advantage of this chemical addition is that pH can be stabilized immediately and the unbalanced population is allowed to correct themselves more quickly. So, because see in the first case we have to wait for few days for feeding of the reactor, but in second stage by addition of some kind of chemical, these chemicals will be mostly alkali, maybe sodium hydroxide or potassium hydroxide addition with different normality we can add to reduce the pH immediately in the reactor. So, we need not to wait for longer period to maintain the pH, but is again depend upon the size of the reactor. If there is a very big size of reactor and maybe size of reactor is 500 tons per day or 200 tons or 100 tons per day capacity, that much amount of chemical utilization would not be possible. So, if you see here the activity, the microbial activity at different pH, you see here the pH from this pH you will find maximum activity of methogenic bacteria. Okay. So, optimum pH range to 6.8 to 7.2. Now, if you see the buffering capacity or alkalinity, an anaerobic digestion process has its own buffering capacity against the pH drop due to the production of alkalinity during anaerobic digestion process. As an example, that the degradation of protein present in the substrate release ammonia, which react with carbon dioxide and producing ammonium carbonate NH4HCO3 as alkalinity. So, because of that also we can maintain the pH in the reactor. So, this could be the reaction. The degradation of salt of fatty acids may produce some alkalinity, and these reactions could be possible like here. This also can be possible. So, this is the sodium alkalinity. Sulfate and sulfide reduction also generate alkalinity. The reaction could be like this. So, here also the carbonates or bicarbonates will get produced. When pH in the anaerobic system drop due to VFA accumulation, the alkalinity present within the system neutralize the acid and prevent further pH drop. If the alkalinity present in the insufficient to buffer the system pH, the external alkalinity addition are necessary. Now, the another factor is a carbon to nitrogen ratio. So, as we know that nitrogen is a major nutrient required for growth of microbe and synthesis of anaerobic acids and protein, which convert into ammonia. Okay. If the nitrogen content is low, microbial population remain less, and it might take longer duration of digest the available carbon present in the substrate, means your HRT will be very high. If the nitrogen content is high, then excess nitrogen lead to production of too much ammonia, which inhibit the anaerobic digestion process. So, this is also another problem. If you have more nitrogen, so ammonia production could be possible. Although this ammonia is good for production to get more alkalinity, but if more production, that is also problematic. The carbon serve as a source of energy and nitrogen controls the microbial population. So, the ratio of carbon to nitrogen is very important in the anaerobic digestion process. So, it is suggested that 20 to 30 is the best or optimum carbon to nitrogen ratio for anaerobic digestion process. Now, another factor is a OLR or organic loading rate. The organic loading rate refers to amount of volatile matter that is fed into a anaerobic reactor. The high OLR alters the digested environment, inhibiting the microbial activity during the initial stage of acid fermentation. So, if you add more amount of organic matter, means more carbon, that is also not beneficial for the degradation process. And increase OLR increases acid former activity as compared to that methane former, leading to high accumulation of fatty acids. So, this is also very important factor, and low OLR leads to neutralization of microorganism, leading to very slow rate of anaerobic digestion process. So, that OLR also has to be optimized in the reactor before starting or before operation of anaerobic digestion process. So, OLR therefore should be optimized based on the type of feedstock and the reactor temperature. So, this study has to be conduct before starting the reactor, and also this OLR will be different for different substrate, because different amount of volatile matters will be available, has to be checked time to time and should find the optimum OLR. Now, next parameter is a hydraulic retention time. So, HRT is the average time that the organic substance remain in the digester. So, HRT affects the biological chemical property of organic substrate. It plays a important role, especially for methogenic bacteria in mesophilic range. It is desired to be long enough to provide sufficient methogenic activity. But this is another problem. If you have long or large HRT, your reactor size requirement will be more. In general, HRT is a shorter for anaerobic digestion at higher temperature and vice versa, mostly depend on to the property of feedstock. So, if you go for thermophilic kind of reactor, thermophilic range reactor, your HRT will be obviously low, and mesophilic, obviously your HRT will be somewhat high. Next is the VFA. So, this is what we were talking. The VFA are produced under the acid forming bacteria. So, accumulation of VFA always affect the anaerobic digestion process by lowering the pH and suppressing methogens. During the acidogenesis phase, two VFAs, namely acetic acid and butyric acid, are known to be a favor to the methane formation. Acetic acid contribute almost 70% of methane formation. So, the important VFA is acetic acid. Few other VFA produced like propionic acid, apart from butyric acid, valeric acid, isobutyric, isovaleric acids, and these contribute remaining 30%. So, VFA concentration is a good indicator for monitoring performance of anaerobic digestion process. So, when you do the laboratory experiments of anaerobic digestion process, I think apart from pH, VFA and your COD change, that chemical oxidant change, that is the measurement of volatile solids. Either we can go volatile solid measurement or COD measurement, and also the VFA measurement also is very important. That is a good monitoring parameter for the anaerobic digestion process. So, what will be the relation between volatile fatty acids with the alkalinity? Let us consider an example of anaerobic reactor showing variation in the concentration of alkalinity and VFA with digestion time. So, like you can see here the different concentration. So, here you can see the green color is the alkalinity and red color is a VFA. This graph shows that the digester has good buffering capacity. Now, because VFA production is less compared to alkalinity. So, low VFA accumulation at 200 milligram per liter compared to the alkalinity of 2000 milligram per liter. So, now we can understand the reactor is a very good buffering capacity. And when you compare the VFA with pH, so let us consider that three different situations of alkalinity and VFA at the same reactor at time A, B and C, and then we will compare the pH of the reactor. So, now here we see that now when you started the reactor, your VFA production was 200 milligram per liter and alkalinity production is 2000 milligram per liter, but at one point the VFA production has increased and alkalinity has been reduced. So, we take three different situations like A, the situation A, B and C. Now, when you see the pH in the all three different situation, we started with the pH of 6.8, but at the situation C or stage 3, pH is dropping and coming to the acidic condition. So, at condition A, the pH is stable. So, in that case alkalinity is more than VFA, and at time B or stage B with increasing VFA. Now, here you see that VFA is increasing, but alkalinity is slightly reducing, and decreasing alkalinity pH still remains stable. So, until that also pH will not affect, because in same condition the alkalinity is more than VFA, but at stage 3 the VFA now is more than alkalinity or almost equal, the reactor natural buffer becoming insufficient. So, pH of the reactor start to fall. Now, take the same example of gas production. So, like we saw in the previous one, at this condition pH has been dropped and when the same alkalinity and VFA conditions, how the methane production could be possible. So, now this also we saw that methane production and carbon dioxide production. So, even there is no change in gas production or methane production until time B, okay, where alkalinity is more than VFA, but at time C the methane production ceased, and after that the methane production will be completely dropped down and carbon dioxide increase will get start. So, see how important is alkalinity and VFA production in the reactor. So, when you monitor or when you operate the anaerobic digester, time to time you collect the sample and get it analyzed, alkalinity also get it analyzed and VFA also is analyzed. Suppose you are not able to do the alkalinity, but at least VFA, total VFA try to get analyzed and see that this concentration should not increase up to 2000, 3000 milligram per liter VFA. So, because not only it will hamper the pH of the reactor, also it will affect the methane production in the reactor. So, thank you, and might you people have understood very well the different stages of anaerobic digestion process, and also there are different factors which is affecting the biogas production or methane production. So, thank you.